Good morning, dear students. Welcome to our session of microwave and antenna. In previous session, we started off with the discussion of antenna basics, in which we discussed what is an antenna and what is a radiation pattern, what is meant by isotropic antenna. Then we discussed regarding basic antenna parameters. Then we had discussion regarding the patterns. That is, what all things come under patterns. What is a radiation pattern? Then under that, we discussed regarding half power beam width and first null beam width. So these are parameters what we had discussed in previous session. Then apart from this, we discussed two problems relating to first null beam width and the half power beam width. So these are the problems what we had discussed in previous session. So continuing with the next part, that is power density. So power density is the power flow through unit area. It is given as the, or it is defined as the power flow through the unit area. So in this, what they consider is, if you consider an antenna at the center, and if you imagine this antenna to be surrounded by a sphere, antenna is at the center of the sphere, and at a distance r, say the radius of the sphere is r, so at a distance r, if you measure the power which is flowing through this unit area, so if this is a unit area, if you measure the power which is flowing through this unit area, that information will give you the power density. So power density is the power flow through this unit area. And when we consider it in terms of antenna, we consider the antenna to be at the center of the sphere, at the center of the sphere. So at the if the sphere radius is considered as r, so it will be at a distance r from antenna. If you consider at a distance r, and if you consider a unit area at that point, and if you measure the power flow through this, if you measure the power flow through this unit area, it will give you the information pertaining to power density. So that is what they have displayed here. That is the area what is considered is perpendicular to the power flow. It is perpendicular to the power flow. So if I measure the power flow through this unit area, it will give me the power density. Now, how is it given in terms of the electric and magnetic field? Power density is given by the cross product of the electric and magnetic field components. So the cross product, when I expand it, what I'll be having magnitude of E into magnitude of H, and angle sign of the angle between E and H, and the unit vector, which is actually in the normal direction to the power flow, or the power density, to the power density. So now we know that electric and magnetic field. So if electric field is present in one direction, magnetic field will be present at 90 degrees. It will be present at, they are 90 degrees apart. Electric and magnetic field are 90 degrees apart. Therefore, theta turns out to be 90 in this case, that is in this cross product. So when we substitute, on sine 90 is 1, therefore what happens is power density is given by, it is given by magnitude, or that is a product of the magnitude of the electric and magnetic field intensity. So therefore we have the power flow, which is the power density. It is a product of the electric and magnetic field intensity. So that is what we have. But we have another parameter, that is the intrinsic impedance. Intrinsic impedance in terms of electric and magnetic field is given by E by H. That is, intrinsic impedance is equal to E by H. And this is also equivalent to permittivity and permeability in which is given by this equation, which is square root of mu by epsilon. If you consider that the electric and magnetic fields are traveling through vacuum, that is in free space, at that time these turn out to be square root of mu naught divided by epsilon naught. So when we have that mu naught divided by epsilon naught, it turns out to be 120 pi or 377 ohm. That is, this is the intrinsic impedance of the free space. That is what we are looking out here. So when we consider the free space traveling wave, then what we have is E by H will be given by 377 ohm or 120 pi ohm. So if I have to represent the previous equation, that is S is equal to E into H. If I have to represent this one, right? S is equal to E into H. I can represent. I can substitute one of these parameters and obtain an equation in terms of either electric field or in terms of magnetic field. For that purpose, I can make use of this equation. So here we got to know that E by H is equal to 120 pi. So here what we can do is, therefore E is equal to 120 pi into H. So if I substitute that, I'll get power density as H square into 120 pi. Or else, if I want to substitute H will be equal to E by 120 pi. H will be equal to E by 120 pi. If I substitute that over here, I'll be getting E square divided by 120 pi. So this is the power density, which is defined as the power flow per unit area or power flow through the unit area. So if I have to measure the RMS value for this one, I'll be taking half the cross product of E and H. Half the cross product of E and H. So next, what we have is a power theorem. So now we saw that what is meant by power density, which is given by, sometimes it is identified by S or sometimes it is given by P, power density. So S is nothing but, it is nothing but again pointing vector. It is nothing but pointing vector. This is nothing but pointing vector equation. So it is identified with S or P. So based on this parameter, we have the power theorem. So as I mentioned, if I consider an antenna at the center of the sphere, and I'm considering that you are measuring those values at a distance of r. So at a distance of r, it implies that this antenna is placed within a sphere of radius r. The sphere's radius is r. So that is what we are considering over here. So here, as per the power density, what we consider the surface of the sphere at a distance r from this antenna, and we consider a unit area over that sphere. And if we measure the power flow through this unit area, I'll be getting the power density what we represented, S or P representation. Now, if I take the integration, that is surface integral, if I take the surface integral of this parameter, that is the power density. If I take the surface integral of this power density, I'll get the power theorem. So by definition, what it happens to be, it is the surface integral of the power density. It is a surface integral of the power density. And in taking that surface integral, what you are doing is you are considering the entire sphere's surface. When you're considering that surface integral, you consider the entire sphere's surface. So when we consider the sphere, right, since it is in the spherical coordinate system, you have three parameters, r, theta, and phi. So we had discussed a few of the parameters related to these coordinates, that is the range. So r is in the range of what? 0 to infinity, and theta is in the range of 0 to pi, and phi is in the range of 0 to 2 pi. So these are the possible values for r, theta and phi. So now again you have to consider a sphere. So with respect to that, the integration parameters you have to check out. So power theorem is given by the surface integral of the power density, in which you are considering the entire surface of the sphere. So when you're considering the entire surface of the sphere, these are the ranges what you will be looking forward. So it is sometimes it is given by W. So this one is nothing but you are taking the surface integral of power density with respect to the surface, with respect to a small elemental surface area. So this is indirectly nothing but it is the total power which is being radiated by an antenna. If I consider it to be in that form, it will be actually the total power which is being radiated by the antenna which is under consideration over here. So I got to know through unit area, through a small unit area, I am getting a power flow of yes. So if I consider the entire sphere, I have to take the integration of this factor. I have to take the surface integral of this factor. So when I take the surface integral of this factor, I'll be getting what is the total power which is being radiated by this antenna. That is the information what I'll be getting. So power theorem basically gives you the information pertaining to total power which is being radiated by the antenna which is under consideration. So here, this is the equation by which the power theorem is given, where W is the total power, which is equal to the surface integral of the of the power density, of the power density. Now here, ds is the elemental surface area. It is the elemental surface area. So now let us see what is actually ds, or elemental surface area, in terms of r, theta and phi. So here we have the representation. So in this case, what we are considering is, we assume that say an antenna is placed at this point, and at a distance r, we are measuring the radiated power. So we are measuring the radiated power. And since we have to consider the spherical coordinate system, what happens is we have to measure it at all the possible points. So when we do that, what happens is we'll be imagining this antenna within a sphere, and this acts as the center of the sphere. So that is how we try to analyze this. So now when we consider this parameter, right, I need to measure this surface area. I need to measure this. So this is nothing but the elemental surface area. So and by definition, what happens is if you measure the power flow through this unit area, that will be equivalent to S. That is power density. If I measure the power flow through this unit area, it will give me the power density. And in this case, I'm considering this small elemental area or the unit area. So in this case, what I have to do is I have to try to see what is this entire area equal to. What is this entire area equal to? So if I know that elemental surface area, right, then if I take the integration of that with respect to the S parameter, then I'll be able to obtain what is the total power which is radiated by the antenna which is under consideration. So here what we do, in order to measure a small elemental surface area on the sphere, so what we do is, so we know that this area is at a distance of r. This area what I'm considering, because we are considering the area of the radius of the sphere to be equal to r, that is the distance at which we are measuring the power. So this all the points on the sphere will be at a distance r. So when we consider this, how do I obtain the elemental values? So for this purpose, right, what we can do is we can consider a cube, and then we can go ahead with the discussion. So how do we obtain these values? Suppose what I'll do is, so if we just imagine a cube over, so we are just imagining a cube, and so whatever values we had, so we are considering x, y, and z. So this is x, this is y, and this is z axis. So antenna is assumed to be at this point. Antenna is assumed to be at this point. So here, if I take from this point to this point, and if I consider this distance to be r, that is the radius of the sphere or the point of observation from this antenna. So this is the point where you're observing. So this is a point on the sphere. So it is given by r, theta, and phi values. It is given by r, theta, and phi values. Now here we can see that we have got r sine theta, then we have got with respect to theta and delta theta, all these parameters what we are forming. So I should know how these values I have obtained. How is this r sine theta? How is this r sine theta d phi? So those all will just try to estimate. So this one, what we have is, so we are considering a point over here which is at an angle theta and at an angle phi. So here we consider the same thing. So this one makes an angle of a phi, makes an angle of a phi, and this one makes an angle theta. So therefore you have r, theta, comma, phi. So these are the coordinates of this point. So with respect to this point, I have to measure few of the parameters over there. So if you just consider this, what happens is we can identify what is this line equivalent to. This line, what we are considering, it is nothing but this parameter what we are trying to identify. So this one gives you that information. So if I measure this right, I'll be able to obtain what is this particular value. So here what I'll get is, so if I measure this, so this is angle theta, this is angle theta, this is r. So if I happen to measure the angle between these two, it will be 90 degrees. So if I consider the right angle triangle, then what I have is with respect to this angle and with respect to this theta, this side will be r sine theta. So if I consider this will be what? It will be r sine theta. So if I consider sine theta, with respect to that, sine theta is how much? Sine theta is opposite upon the hypotenuse. Opposite upon the hypotenuse, that is this value. If I just assume that this is A, so it will be A by R. Therefore, the length of this one is A, which will be given by A is equal to R sine theta. So similarly, so this, if this is R sine theta, even this is also R sine theta. Even the value of this one is also r sine theta. Now, any other angle we can measure. So if we just observe, if I know that this is r sine theta, if I know that this is r sine theta, this is angle phi. So if I consider sine phi, right? So if I consider this value to be b, So B will be given B in this case. So what we have, sine phi will be given by opposite upon the hypotenuse, that is r sine theta. So therefore what happens is this will be equal to r sine theta into sine phi. So this side will be r sine theta sine phi. So since it is a cube, all sides will be r sine theta sine phi. So this is the angle what we'll be getting. So once we have obtained one parameter, that is this part. So here what is this indicating is, so if I measure it from this point to this point, I have r sine theta, or this one to this one, it is r sine theta, because I'm considering a constant angle over here. So now here, if I measure this point, right, I have that is based on the sphere we had observed it. So we had observed it based on this sphere value. So I obtained this parameter that is of importance for me now. So now what we are doing is, if there is an elemental increase in this theta, if we consider an elemental increase in this theta, that is this d theta value, this is the elemental increase what we are considering. So what happens is, we'll be having theta and theta plus d theta. So this one gives rise to theta, or delta value of theta. So what is this side equal to? So whenever you have something in this form, so and this angle is very small. This angle is very small. So this is d theta, and this side is r. This angle is very small, then this side is also nearly equal to r. Therefore what does this the length of this one equal, length of this one will be length of the small arc, it will be equal to r into d theta. So that is the concept what you are applying over here. You are applying that concept over here. So therefore the side which you observe is r into d theta. So this side I got r into d theta, this one I got r sine theta, r sine theta. And how do I obtain this parameter again with respect to this one? So what you're considering over here is, you are considering phi up to this point, and you're increasing it by slight amount, so by delta phi. So this angle is delta phi, and what I want is, I want to measure this side. So if I measure at this point, right here only, if I measure, so it will be a radius into the angle, so it is r into delta phi. But when I go to this point, right, this one varies with the function of theta also. So therefore what I have is, in this case, when I project this, so this side what I am getting, when I project this side what I am getting is actually given by r sine theta, here r sine theta. So this one what it turns out to be is, the small arc will be r sine theta, and the small elemental change of the angle, so that is, this is r sine theta d phi. So here two parameters what we have obtained is r sine theta d phi, and this one is r into d theta. That is what we have looked out for. So we have to, once we know the side of these two, right, once we know the side of this square box, then the elemental area is nothing but r into delta theta into r sine theta d phi. So multiplication of these two sides will give you the elemental area. So it is noted as ds or sometimes dA. So this small elemental surface area will be given by r into delta theta into r sine theta d phi. So when I simplify it, this is what I'll be getting. That is r square sine theta d phi. R square sine theta d phi. So this is a small elemental area or the surface on the sphere. So what we have considered, which is given by r square sine theta d phi. So now, so if I have to, that is what we have measured over here. That is dA or ds is equal to r d theta, and the other parameter is the other side, that is r sine theta d phi. So when I simplify this, this is the small elemental surface area in terms of r, theta and phi. So it is given by r square sine theta d phi. So now what we can do is we can substitute this in the previous equation, that is the power theorem equation. In this equation, I can substitute what is ds. So if I substitute that, what I'll be getting is I'll be getting W, which is surface integral of P into R square sine theta d phi. I am substituting ds in that power theorem. So when I substitute, I get R square sine theta d phi. So now what will be the angle? What will be the limits of theta and phi? So now in this case, right? So in this case, if I just consider it in this form, right? So here, what I am having the sphere. So I am having the sphere. So if I consider this entire sphere for the estimation of this power, if I consider the entire sphere, that is the full sphere, if I consider this, then the angle theta will vary from theta will be the elevation angle. It will vary from 0 to pi. So it will be 0 degrees to 0 to pi radians. That is 0 to pi. This will be theta. And what about the phi variation? So if I consider over here, what happens is phi will be varying from 0 to 2 pi. So in this case, what is happening? I am considering the entire sphere. So if I consider the entire sphere, I'll be getting the power which is given by integration of phi is equal to 0 to 2 pi, theta is equal to 0 to pi, which is given by p into r square sine theta d phi, where p is nothing but the power density. Power density. Now there is another thing to be considered, that is when I consider the half sphere. So if I consider only the half sphere, right? So what happens? So if I consider only half sphere, you can observe that, say if I consider this or this, any one. So if I'll just for simplicity, I'll just consider one of them. So when so what happens is if I consider the theta variation, theta will be varying from 0 to only this point. That is from 0 to pi by 2. Even if I consider this, it will be like 92 only from this point to this point, that is it is only 0 to pi by 2. It is symmetric. It is symmetric. So only on one side you have the radiation present, other side you have no radiation. That is how it is read. So if I consider this, right, in semisphere, in this half sphere, right, it will be from 0 to pi by 2. It will be pi by 2. But what about the angle phi? So if I measure, it will be the entire 0 to 2 pi. So phi in this case, that is the azimuth angle. So here if you just observe, here if you just observe, for azimuth angle, that is phi, it is in the angle limit is 0 to 2 pi. But for elevation angle, it is 0 to pi by 2, because you are considering only the half sphere. You are considering only the half sphere. So it will be the angle will be varying from 0 to pi by 2. So here it will be integration with these limits. It will give you the total power when you're considering only the half sphere. So this one you'll get to know why you have to consider this, because you have something called as unidirectional antennas and non-unidirectional antennas. That is, whenever we consider an antenna which radiates only in one particular direction, and some of the antennas radiate in say different directions at the same given time. So if we consider those, right? So if it is only unidirectional, then I go for this case. If the antenna is unidirectional, then I go for this case, or else I'll be going for the other one. That is, I'll be considering the full sphere. If the antenna is unidirectional, I'll be considering the half sphere. So it is like, you have an antenna. Say for example, you have an antenna which is placed over here, and below the sphere there is no radiation happening, but only above this point, that is only in the half this thing, when you measure, you are able to obtain the values. Below this thing, you are not obtaining the values. So in this condition, what happens is the theta varies from 0 to pi by 2, and the angle phi varies from 0 to 2 pi. So under these conditions, the total power which is measured will be altered. Okay, so therefore you should identify the limits what have to be considered. So this is power theorem, in which helps us to identify the total power which is being radiated by the antenna which is under consideration, and that antenna we are considering to be placed at the center of the sphere. And based on that, if you substitute the elemental surface area, you'll be able to obtain whether we have to consider the full sphere or the half sphere. A full sphere will be considered for non-unidirectional antenna, and half sphere will be considered for unidirectional antenna. So this is with respect to the power theorem. So now we have something related to solid angle. So that we'll be again discussing in the next beam area concept. So here, what is actually beam area or beam solid angle? So here, whenever we consider the polar coordinate system or the spherical coordinate system, so here we saw that we obtained the elemental surface area as r square sine theta d theta d phi. So here, if you just consider this element, so this is nothing but multiplication of two angles. One is sine theta d phi multiplied with the small delta angle. So here, if you just observe what you have. So here you can observe that this is given by r sine theta. This one is given by r sine theta d phi. So here this part gives you the angle information, and in this case d theta gives you the elemental angle information. When I multiply these two elemental angle information, right, I'll get what is known as elemental solid angle. I'll be getting what is known as elemental solid angle. So this one is sometimes represented by d omega, which is called as elemental solid angle. And this angle is actually subtended by the radiation which is being emitted by the antenna. So that is the information what it gives. So sine theta d phi is actually equivalent to d omega, which is the elemental solid angle. So now what does this solid angle information give me? So this information indirectly for radiation pattern, right, gives me the information pertaining to the beam area or the beam solid angle. So how do I obtain this? So before going into that, we have to consider this parameter. So previously we had seen that the elemental surface area is product of r d theta into r sine theta d phi, which turns out to be r square sine theta d phi. And when we represent this elemental surface area in terms of beam area, it will be r square d omega. It will be r square d omega. So omega range, omega can range from 0 to 4 pi. Solid angle can range from 0 to 4 pi. So let us see how this actually comes out. So here it is actually the d omega is specified as the solid angle which is subtended by the elemental surface area. That is, in previous this thing you are considering the small elemental area, right? This part you are considering this part, what is the solid angle subtended by this small elemental area, that is given by d omega. Now basically what solid angle tells us is, it tells us how large the object is when we are viewing that object from that point. So for example, if I want to identify how big the sun is, so I can measure the solid angle with respect to the observer and tell that this is how big the sun appears. So I can give how big the sun is based on the solid angle. So sun is also sphere, but what I am doing is I am considering it in terms of the solid angle. So solid angle is actually a two-dimensional angle. It's a two-dimensional angle. So if you just see, it is a multiplication of sine theta d phi with d theta. So that is what you can observe from this equation. It is that part. So it is basically a two-dimensional angle for representing a 3D object. Sun is a three-dimensional object. So if you want to identify how big it is, you can measure the solid angle which is subtended by that sun. So you are at observing point, you try to measure what is the solid angle subtended by that sun. So when you consider that, that gives you the information of how large the object is. So in this case, why that becomes important now, or why we have to consider the solid angle. Now in previous this thing, right, what we had seen, we had seen the radiation pattern, right? We had seen the radiation pattern. So it was something in this form, this form. So if you consider this one, right, just for example, so if you just consider this, right, so this is a three-dimensional parameter. Radiation pattern is actually related to three-dimensional parameter. So here, if you consider talking on a phone, your cell phone, so what happens is you can just move around and you can capture the information. Suppose you are exchanging information on Bluetooth. So Bluetooth is accessed via the antennas. So if two devices are being connected and you try to access the information, that is you are trying to send the information to the other device and other device is accepting it. Even though if you are roaming around through that Bluetooth, you'll be able to receive the data. At sometimes what happens is you might see that the data transfer will be happening at a very fast rate or a very small or lesser rate, or the strength might be weak. So you might have observed these things. So it is all because of the radiation which is being emitted by the antennas of the mobile phone. So when we represent how much radiation is being emitted by a given antenna and plot it, I might get it in a three-dimensional form. This is just an example what they are showing. This is not exactly for the antenna. So it might be even for it might be even in this form. It might be in this form. Radiation pattern, it can be in this form. It can be in this format. So depends on when you can observe it based on how it is actually emitting. So here when you consider it, right? So how large this radiation pattern is, I want to measure how effective it is or how large it is. So if I make a person to stand at this end, so if a person is standing at this point, or if an antenna is present at this point, how this antenna will be looking at this radiation, how this antenna will be looking at this radiation. That information will be given by the solid angle, which is subtended by this radiation pattern. So this is like you have a balloon and you hold the balloon in front of you. So you'll be able to see only that circle part of this radiation. You'll be able to see only that circle part of the radiation. So that circle part, how large it is. So that, and but it is a 3D pattern. But it is a 3D pattern. So how large it is? If it is a two-dimensional, then you could have measured the area. But it is a three-dimensional parameter. You have taken a balloon and placed in front of you. So we take a balloon and we place it in front of you. And when you observe from the other end, it might look a two-dimensional parameter. But actually it is a three-dimensional parameter. So how do I measure how large that object is when we are considering this factor? So when we consider that, what happens is it gives us the information related to the radiation. So that's why you have to deal with the solid angle. So in this case, sine theta d theta d phi gives you the d omega value, which is the elemental solid angle. So what is solid angle? In short, solid angle itself is defined as the two-dimensional angle in 3D space that is subtended by the object. It's a two-dimensional angle in 3D space that is subtended by the object. So that is, for example, I took the example related to how big the sun appears. So which is given by the information pertaining to the solid angle subtended by that object, that is the sun, what I had considered. So if I have to define it in a solid angle in other form, then what I do is I can define it, I can specify that it gives you the measure of how large the object appears to an observer who is looking from that point. So that is what solid angle in gives solid angle gives you the information. And now when we are considering solid angle, right, we define beam area. So beam area is also sometimes termed as beam solid angle. So what is this beam related to? This beam is nothing but the radiation pattern what you are speaking of. So beam area gives you an information pertaining to the radiation patterns information. Radiation patterns information. That is how large the radiation is when an antenna is observing it. So which is identified with omega A. And what is omega A given by? So let us look at the equation and then come back. Omega A is given by the surface integral or the integral of normalized power with respect to the solid angle. Beam area is, or beam solid angle is the surface integral of the normalized power density with respect to the solid angle, with respect to the solid angle. So here, this is the normalized power. What is d omega as per previous case? D omega is sine theta d phi. It is sine theta d phi. So therefore, when you substitute it, omega A can be represented in terms of theta and phi, which is product of, which is the integration of this normalized power density with respect to sine theta d phi. So now here what happens is phi is in the range of 0 to 2 pi and theta is in the range of 0 to pi. And as I mentioned, that solid angle range is 0 to 4 pi. Now, how this actually 4 pi comes? How this 4 pi comes? So here we can observe. First, I should measure what is the area of the sphere. So in general, I know what is the area of the sphere. Area of the sphere is given by 4 pi r square. It is given by 4 pi r square. So here previously we measured some parameter over here. That is, if I happen to measure the area, right, this is given by what? R square sine theta d phi. It is r square into d omega. So whatever elemental surface area we are measuring, so area will be given with r square into d omega, which is related to this small elemental surface area of the sphere. So now what is the area of the sphere? Area of the sphere is 4 pi r square. So now if I compare this one with r square d omega, r square d omega. So this omega is nothing but the solid angle which is subtended by this sphere. So in this case, this area is related to the entire sphere what we are speaking. It is related to the entire sphere what we are speaking. So this equation what we are considering is here this 4 pi. What we have is this 4 pi is nothing but the solid angle which is subtended by the sphere. Solid angle which is subtended by this sphere. And sphere is the element which subtends the highest solid angle. No other element subtends more than the sphere. So sphere subtends the highest angle, highest solid angle, so which is 4 pi. So as per this representation, right, this 4 pi is nothing but the solid angle which is subtended by the sphere. So therefore 4 pi is the solid angle which is subtended by the sphere. And what is the unit of solid angle? What is the unit of solid angle? So in this case, right, a angle solid angle SI unit is steradians. In short, it is noted as SR. It is steradians. And we have one steradian is actually equivalent to 1 radian square. It is equivalent to 1 radian square. So how do I get this information? You can observe in this case, you can observe over here. So what you have, so here you are multiplying what? R sine theta d phi and R d theta. So it is R square sine theta d phi. So d theta is a elemental angle, d phi is also a elemental angle. So if it is, and SI unit of angle is what? SI unit of angle is radian. SI unit of angle is radian. What is radian multiplied with radian? It will give you radian square. It will give you a radian square. Therefore, unit of solid angle is actually radian square, but in SI unit, it is identified with steradian. So solid angle is given by steradian. So therefore, what happens is 1 steradian is equal to 1 radian square. 1 steradian is equal to 1 radian square. So this one I can write it as 1 radian into 1 radian. So this is nothing but 1 steradian itself. So since it is 1, right, so it will not create any problem. 1 radian into 1 radian. So it is 1 radian square, which is nothing but 1 steradian. Now, what is 1 steradian equal to in terms of degrees? 1 steradian equal to in terms of degrees. So now what you do is you convert this radian into its equivalent degree. So in this case, what you have 1 radian. So this 1 radian is actually equivalent to 180 degrees divided by pi into this 1 radian value. 180. So this one is 180 divided by pi. Similarly, the other one is 180 divided by pi. So when you solve this, you will get 1 steradian equal to in terms of degrees. So here this one is related to a degree, this one is related to a degree. Therefore, in this case, what happens is we'll get square degrees. So 1 steradian I'll be getting in terms of square degrees. So what is 1 steradian equal to? So here we have measured it. So it is 180 by pi. So 1 steradian is equivalent to 3282804 square degrees. Since it is degree square, we write it as square degrees. So 1 steradian, how you are getting 3282? Again, remember 1 steradian is actually equal to 1 radian square. But what is 1 radian equal to? It is 180 divided by pi degrees. So it is 180 divided by pi. So this is in terms of degrees. When you take the square value, what happens is degree square you will be getting 3282.81. So this is the value of 1 steradian in terms of degrees. So here what you're having, 1 steradian is equal to 1 radian square, which is equal to 3282.81 square degrees. So this is the value, and this is how you represent it. square degrees instead of writing square degrees every time. So whatever value you get, 3282, what you have got, you represent square degrees with the square in the superscript, with the square over here. So this is how you represent it. So this is with respect to the steradian representation. And here we got to know that what is the solid angle which is subtended by the sphere, which is equal to 4 pi, which is the maximum solid angle which is subtended by any object. So no object will subtend an angle which is greater than that. So therefore, the solid angle subtended by any object will range from 0 to 4 pi. It will range from 0 to 4 pi. Solid angle is measured in terms of steradians. So that is what we have discussed. So we got to know that one steradian is actually equal to 1 radian square, which is equal to say 3282 square degrees. Now what is 4 pi steradian equal to? So this we can measure it from this parameter. One steradian is 3282 square degrees. Therefore, 4 pi steradian is equal to how much? So you just multiply 4 pi with 3282 square degrees. You will get this representation in terms of square degrees, which is around 41,000. So it is around 41,253. 41,253. So remember, in terms of steradians, 4 pi is the solid angle which is subtended by the sphere, and in terms of radians it is 4 pi radians square, and in terms of square degrees it is 41,253, which is square degrees, which is a solid angle which is subtended by the sphere. So this is the information pertaining to the beam area and the beam solid angle. So beam solid angle omega A is given again by the integral of the normalized power. So remember, this one is the normalized power with respect to the solid angle. So wherein this d omega is nothing but sine theta d phi, which is given in terms of steradians. So this is with respect to beam area. Now beam area is also given by one of the approximate equations. So this is actually called the exact equation. This is the exact equation. This we term as the exact equation. We have another way to identify the beam area, which is with respect to the half power beam widths for a given pattern. So it is given by this one, wherein it is defined as the product of the half power beam widths in theta and phi directions respectively for the given radiation pattern. For the given radiation pattern, the product of the half power beam widths in theta and phi directions gives us the beam area. So this is actually a approximate equation. This is called as the approximate equation. So this is the exact equation. This is the approximate equation. So we have actually problems pertaining to this. We'll be discussing this regarding in the next session.